Hello and welcome to the 15th lecture of analog integrated circuit design. In the previous lecture we discussed the two stage op amp in great detail, so where the poles and zeros were and tried to adjust the components so that we get a sufficient phase margin when the op amp is placed in feedback. Okay. Now, to not worry about exactly what feedback loop the op amp is placed in, we assume that it is placed in a unity feedback configuration and then go with the calculations. In reality, what you have to do is to find the value of k, that is the feedback factor that you are trying to use in the actual circuit, and then do your loop gain calculations based on that one. Okay. Just a quick recap. This is our two stage op amp. The first stage GM1 has an output resistance R01 or an output conductance G01, and there is a capacitance C1 here which can be due to various sources. And the second stage has a transconductance GM2, an output conductance GO2 and a total capacitance of CL, which can be due to transconductance itself and any load that is applied to the op amp, and there is a capacitance C which is around the second stage, and this is the integrating capacitor, that is the current from GM1 is supposed to pass through this and give the integrating function with a unity gain frequency of GM1 divided by C. Okay. And we also evaluated the expression for poles and zeros and all that stuff of this one. The DC gain is the product of the two DC gains. The low frequency pole is at minus GO1, that is this conductance divided by the total capacitance, which is C1 and Miller multiplied C. Okay. And the second pole P2 is at the total conductance is GO2, but more predominantly the effect of GM2 in feedback. And here we have total capacitance, which is CL plus C and C1 in series. Okay. And the 0 is in the right half plane at GM2 divided by C. Okay. We also saw that the second pole can be further approximated by, this is when C is much more than C1, GM2 plus GO2 divided by CL plus C1. Okay. Now, GM2 is expected to be much more than GO2, so we can neglect this as well, and usually CL also many times happens to be much more than CO1. So, this can even be further many times approximated by GM2 by CL. Okay. Now, what is our stability criterion after all? The unity gain frequency of this is of course GM1 divided by C. Our stability criterion says that the 0 and the pole has to be sufficiently beyond the unity loop gain frequency, which is the same as the unity gain frequency of the op amp for a unity gain amplifier. Now, the phase lag contributed by the 0 is simply a function of the ratio of GM2 by GM1, and that has to be maintained sufficiently high, so that the phase lag is small. The phase lag due to the pole will be something, and we would like P2 to be much more than omega u. Okay. Now, what does this mean? Remember, this op amp was derived from a structure like this. Okay. We wanted the output current of GM1 to go through a capacitance C, and we found that the best way was to implement a current controlled voltage source. Okay. and this current controlled voltage source is implemented using a some op amp, okay, shown here in red, and let us say it has a certain frequency omega u 2. We also know that if you take an op amp with a unity gain frequency omega u and you make a feedback circuit with it, then the feedback functionality will be okay until a frequency of the unity loop gain frequency. Okay. Below the unity loop gain frequency, the feedback loop functions as it is supposed to. Above the unity loop gain frequency, the loop gain becomes very small and clearly the feedback loop does not function as desired. Now, what does it mean? The unity loop gain frequency of the second feedback loop turns out to be omega u 2 itself. So, omega u 2 has to be sufficiently larger than the frequencies of interest. Now, what is the frequency of interest? We can consider omega u itself to be the frequency of interest. What by this what I mean is, we are trying to make an op amp with a frequency with a unity gain frequency of omega u. Okay. That is, this entire circuit should behave like an integrator up to a frequency of omega u. Now, the integrator itself is made by placing a capacitor around the second op amp, so that we form a current controlled voltage source. Now, this will behave like a current controlled voltage source only below a certain frequency omega u 2, which is the unity gain frequency of the second op amp. Now, clearly the unity gain frequency of the second op amp has to be more than the unity gain frequency that we want to realize. Okay. If this is not the case, then clearly the entire circuit does not behave like an integrator at all. Okay. So, the integrator has to behave like an integrator, that is have a 20 dB per decade roll off at least up to the unity gain frequency of the integrator. Okay. So, this is what we would guess just by looking at this sort of system block diagram. Now, what is omega u 2? It is the unity gain frequency of the second op amp and it is GM2 by CL. Okay. Clearly, then GM2 by CL has to be much more than the unity gain frequency we are trying to realize, which is GM1 by C. Okay. So, that is this frequency here must be much more than GM1 by C, and that is exactly what this condition is saying also. This P2 has to be much more than omega u. The second pole P2 appears because the op amp with which we made the current controlled voltage source itself has a finite unity gain frequency. If the unity gain frequency of this the second op amp was infinite, then we would not have the second pole and we would just have a single pole op amp. Okay. Is this clear? So, this gives you another intuitive way of figuring out why these conditions come about. It is extremely important when you get algebraic results to attach some intuition to it. Okay. Now, the right half plane 0, this causes phase lag. Okay. Now, this is an annoying problem as well, because of this the phase margin is deteriorated. Now, if we did not have the right half plane 0, we would have the phase lag only due to the poles and it would have been a better situation. Okay. That is, you have less phase lag because you do not have the right half plane 0. So, what we would like also is to investigate if there is a way of getting rid of the right half plane 0 or maybe eliminating the effect or reducing the effect of the right half plane 0. Okay. Now, in order to do this, let us first figure out why the right half plane 0 comes about. For this, I will focus only on the second stage of our op amp. Okay. We have a current GM1 VE that is supplied by the first transconductor, and that is passed through this current controlled voltage source, which behaves as an integrator. Okay. Now, what I will do is I will neglect all the other components because I want to focus only on the right half plane 0 and not worry about other details. Now, what happens if we do this? This GM1 VE will pass through the capacitor and it causes a voltage drop GM1 by SC times VE, and this is exactly the voltage that we want, but this is not the voltage that appears as VO, because that is equal to the voltage across the capacitor plus the voltage between this point and ground. Okay. And this will have a voltage. Now, I have assumed that there is no load or anything like that. So, this GM1 VE, this current passes through the capacitor and has to come out of the transconductor. If it has to come out of the transconductor, across this there must be a voltage which is equal to the current through the transconductor divided by the transconductance value, which is GM2. Okay. So, the total voltage V naught equals GM1 VE 1 over SC minus GM2. Okay. Sorry, minus 1 over GM2. Now, this is what results in the right half plane 0. This is exactly the term we saw in the numerator earlier also, and that is what gives you the right half plane 0. Okay. And we want to get rid of this one. Now, by looking at the expression for VO, we can guess what we must do to get rid of this. The expression for VO is the input current to the second stage, which is GM1 VE times 1 over SC, which is the desired term, minus 1 over GM2, which is the undesired term. Okay. If we had only the first term here, we would have an integrator of unity gain frequency GM1 by SC, right. So, what can we do to get rid of this? We have to add plus 1 over GM2 in some way or the other. So, we have to add this term for eliminating the right half plane 0. Okay. If we do that, then this simply cancels with that and we will be left with only the integrator. Now, how do we add that? So, that means that to the output voltage that we originally have, we need to add a voltage equal to GM1 VE divided by GM2. Okay. That is the input current divided by GM2. Now, there is a very simple way of doing this. That is the voltage that is developed there. This is GM1 VE, and this branch, the capacitor, also carries a current GM1 VE. Okay. So, I want the voltage to be the voltage across the capacitor plus this plus an extra term, which is GM1 by GM2 times VE. Now, it is very easy to see that if I insert a resistor here, which is equal to 1 over GM2, what will happen? Across this resistor, I will have GM1 VE by GM2. Okay. So, now if I sum these three voltages, the voltage across here plus the voltage between these two plus the voltage there, I will get V naught, and V naught happens to be just equal to GM1 times VE by SC. Okay. This is fine. So, by placing a resistance in series with the capacitor, we can eliminate the right half plane 0, and the value of the resistance has to be 1 over GM2. Okay. Now, if the value of the resistance changes from 1 over GM2, what will happen is you will get some not an exact cancellation of the 0, but something else that we can also see. So, let us assume that again the same circuit, and I will call this RZ Okay. The voltage at the input of the transconductor is Gm1 VE by Gm2. The voltage across this is Gm1 VE RZ, and the voltage across that is Gm1 VE by SC. So, the total output voltage is Gm1 VE times 1 over SC plus RZ minus 1 over Gm2. Okay. So, we will get Gm1 VE that, and okay. So, I will write this as Gm2 RZ minus 1 times SC. So, the numerator there is a 0 and the 0 is at Gm2 divided by Gm2 RZ minus 1 times C and the negative of that one. So, this expression makes sense because first of all when RZ is 0, that is the old case, we have a right half plane 0 at Gm2 by C. When RZ is exactly equal to 1 over Gm2, the 0 moves to infinity, and when RZ is more than 1 over Gm2, we will have a left half plane 0. Okay. So, in fact, you can move the 0 to the left half plane, and the advantage of a left half plane 0 is that it offers a phase lead instead of a phase lag, which enhances stability. Okay. But we can't play this game very much, we will see soon why, but at least we see that we can move the 0 to infinity or otherwise manipulate the position of the 0. Okay. Now, this particular structure is very simple, I have eliminated C1, C, Cl on the other side, etc., etc., but the principle works in exactly the same way. Okay. We will see that soon. The principle of 0 cancellation works in exactly the same way and is also widely used. Okay. So, here then is the topology of the two stage op amp with a right half plane 0 cancellation. Now, the transfer function of this can be evaluated in exactly the same way as before by writing the node equations, and before we do that we should again see what is the number of poles and zeros we have. Okay. What do you think? Is it exactly the same as before? One difference from earlier case is that earlier also we had 3 capacitors, but the 3 capacitors were in a loop. So, the sum of voltages of 2 capacitors was equal to the voltage on the other capacitor. So, we could only set 2 of them independently and the third one was automatically fixed. Now, because we have this RZ in series with C, we can set all 3 of them independently. So, this really has 3 poles. Okay. Now, this again is something that keeps happening in design that you should be aware of. Whenever you try to fix some problem, some other problem may come up. It may or may not be severe, but it is something to be investigated. Here what did we try to do? We tried to eliminate the right half plane 0 because it was causing phase lag. We got some technique, and then when we finally put it in the op amp, we see that okay, we may not have a right half plane 0, but we will have an extra pole which also causes phase lag. So, you have to evaluate it more thoroughly to see that the phase lag caused by the extra pole is not ruining the advantage you got by eliminating the 0. Okay. Now, I will not solve this completely, but I will outline the method. So, again we can write the node equations, and I will write it in terms of the same two node voltages as earlier, V 1 and V o equals the source current vector. Now, all we have to do is, earlier between these two terminals we had just C, okay, which gives you an admittance S C. So, in the admittance matrix now, wherever we have S C, we have to replace it by the admittance of this whole thing, which is what? Which is 1 over the series combination of R Z and the capacitor. In other words, this is S C 1 plus S C R Z. Okay. This is an easy way to do it. We could define this to be a node and write node equations, but that unnecessarily makes things complicated. So, the equations turn out to be that is the total admittance loading the first node, total admittance loading the second node, like that, and then here we will have okay, and finally there we will have the source vector remains the same. Here we have minus G m 1 V e and 0, okay. And by taking the determinants you can find the solution. You will find that the 0 will be at what we determined earlier, that is minus G m 2 by G m 2 R Z minus 1 times C, okay. So, if R Z equals 1 over G m 2, the 0 is at infinity. If it is less than 1 over G m 2, it is in the right half plane, and if it is more than 1 over G m 2, it will be in the left half plane, okay. Now, we will also have a third pole, and again by using a similar approximation as before, that is earlier to solve the quadratic equations we took two terms at a time and turned it into two linear equations. Exactly the same thing can be done for the third order equation that we have. If you have a s cube plus b s square plus c s plus d equals 0, you can take these two at a time, equate that to 0, these two at a time, equate that to 0, and these two at a time, equate that to 0. You will get three linear equations, and solution to this will be valid approximation to the actual solution only if the three poles are very far from each other. The magnitude of the three poles have to be very different from each other, okay. Now, if you do that, you will find that the value of the first two poles are almost the same as before, and you will also get a third pole. Now, I will not do the algebra here, you can take it as an exercise and do it. Please make sure that you solve this completely by using the Kramer's rule or whatever your favorite method of solving the matrix equation is, and then do the approximate solution of the third order equation and find out the poles. Now, I will just tell you an intuitive way of finding out the poles. Let me copy over this diagram. Now, the first pole will be associated with GO1 and the total capacitance that we see, it will be almost the same as before. There may be some terms due to RC, but they will not be dominant. Second one will again be due to GO2 and the capacitance associated with that, and the third one will be due to RZ and the capacitances associated with that one, okay. So, what do we have there? We will just have, turns out RZ, C, CL, okay, and C1, okay. In a way, you have an RC circuit involving this RZ and these three capacitors in series, because after all this is just ground and these two are together, okay. So, the pole associated with this turns out to be minus 1 by RZ and the series combination of the three capacitors, which is just 1 over C plus 1 over CL plus 1 over C1. Okay. That is the approximate value of P3. Okay. Now, if you do the third order equation and the approximations that I mentioned, you will get exactly this solution. Please verify that. Please just do not take this for granted, and also try to understand how I got this value here. Now, what did we have? What is the effect of putting RC there? We can eliminate the right half plane 0, but we will end up with a pole. Okay. The right half plane that we, let us say we choose RC to be exactly 1 over GM2. Okay. Then the right half plane 0, it goes away, but we will have a new pole. What is that? It is given by that one. The pole is at minus GM2, because we chose RC to be 1 over GM2, 1 over C plus 1 over CL plus 1 over C1. Okay. And where was the right half plane 0 that we eliminated? It was at GM2 by C. Okay. Now, comparing these two, you see that the pole that you introduced is at a higher frequency compared to the 0 that you eliminated. So, we are still safe. The 0 that you eliminated removed some phase lag, the pole that you introduced introduces some phase lag, but because the pole you introduced is at a higher frequency, it introduces less phase lag. Okay. Now, that is why it is not a very wise thing to make RC very large, because you may think that, oh, by making RC very large, I can move the pole into the left half plane and then even produce phase lead. But what happens is, you will also have this additional pole, okay, which will cause extra phase lag, and you will have a complete washout. And the extreme cases, when let us say RC is infinity, then you will not have this capacitor here at all. You will have these poles very close to each other. Earlier we saw that when this branch was not there, when C was not there, there was some pole frequency here and something else there, and when you introduce C, they moved further apart, which is good for stability. Now, if you make RC equal to infinity, that is very large, then you will go to the original case where the poles are relatively close to each other, which is very bad for stability. Okay. So, it is not a wise thing to make RC very large. It is okay to make it try and cancel the RSP 0. Now, later you will also see that you cannot make component values exactly. You will not be able to make two unlike components have a relationship like this, RC equal to 1 over GM2. So, even if you nominally make it like this, it will vary in one or the other direction, but it is still a good thing, because it reduces the total phase lag that you would have got. Okay. So, it is a good technique, but do not try to overdo it, that is the message. So, that summarizes the two stage op amp. It has a DC gain equal to the DC gain of the two stages, and when you have resistive loads, you can optimize the DC gain of the first stage and let the second stage have a modest gain. This you could not do with a single stage op amp. The single stage had to provide all the gain. With the two stages, you also get this additional complication of extra poles and zeros, but it is possible to design the values so that you have a stable op amp. Okay. Now, let us revisit how we got the two stage op amp. First of all, let me start with the simplest op amp that I had. Which is just that one. Okay. Let me just name them, or let it be like this. Now, the two stage op amp, what did I do? I tried to make it better by using a current controlled voltage source instead. I wanted this to be an ideal op amp, but clearly that is not possible. This is the current controlled voltage source, and I used my single stage op amp in place of that op amp. Okay. And I ended up with the topology, which was the two stage op amp, which of course is that. Okay. By substituting the single stage op amp in place of this one, which realizes the current controlled voltage source, I got the two stage op amp. And I also showed that the two stage op amp is better than the single stage op amp because it offers higher DC gain and so on. Now, I can play this game further, right. I know that if this were an ideal op amp, I would get ideal integration from there to there, but of course, I do not have an ideal op amp. But instead of using a single stage op amp which is inferior, I could try and use the two stage op amp over there. Okay. So, that may give me better results, right, because after all two stage op amp is better than the single stage op amp. Using a two stage op amp here has to give me better results than using a single stage op amp. Okay. So, that is what I will do here. I will redraw it with this op amp being a two stage op amp. Okay. So, first let me draw the two stage op amp. I will call these G02 and C2 and G03 and C3. Okay. And I will have, let me call this C2. Now, this forms my two stage op amp. Okay. And I have plus here and minus here because that is the sense I want to implement the current controlled voltage source. Now, this is my current controlled voltage source, that is this part of the circuit, and I drive it with what I had earlier. I will call this GM1. It could have an output conductance G01 and there will also be a capacitance C1 over there. Okay. Sorry, this is not grounded. This is the input to the op amp V. Okay. So, all I did was I know that a transconductance driving a current controlled voltage source gives me a good op amp, and how do I make the current controlled voltage source? I made it with the best op amp I have now, which is the two stage op amp. Now, this entire thing will give me the three stage op amp. Okay. And in fact, we can go further. In practice, it is not done, although you can have even 4 or 5 stages, right, and get better and better results. What is better about it? First of all, the reason we went to multiple stages in the op amp is to get higher DC gain. The DC gain that you could get from the first single stage op amp was not good enough. What is the DC gain of this stage? If I open circuit all capacitors, I open all of these things, I will simply have GM1, GO1, GM2, GO2, let me label these things, GM2, GO2, and this is GM3 and GO3, all of them in cascade. So, the DC gain will be the product of the DC gains of the 3 stages. Okay. So, this clearly is better than what we could get with a 2 stage op amp, because there we had only product of 2 stages. So, let us say each stage has potentially has a maximum gain of 50, then with a single stage op amp you can get a gain of 50, the 2 stage op amp 2500, and with a 3 stage op amp 125,000. Okay. So, that is what is advantageous about the 3 stage op amp. Now, of course, you can write the node equations for this. There are 3 independent state variables in this case. Okay. I will call it VO, maybe V2 and V1, and you can write it down and analyze it, and such an analysis is necessary for the complete design, but the expressions will be so complicated that we will not have any insight from them. Okay. So, I will only intuitively derive some conditions. First of all, the unity gain frequency of the op amp that I am trying to realize is GM1 by C. Okay. Now, the unity gain frequency of the two stage op amp used for the current control voltage source is GM2 by C2. Okay. Sorry, I had used uppercase GMs here. This is GM1 by C and GM2 by C2. Now, clearly the current control voltage source has to function as a current control voltage source over a frequency range beyond GM1 by C. Okay. Only then we will get this integrating action, that is transfer function of GM1 by SC from the input to the output. So, this clearly means that GM2 by C2 has to be greater than GM1 by C. And this two stage op amp itself is made using a current control voltage source. So, I think I called this CL earlier, let me go back to the terminology. CL consists of any capacitance here plus external load that is applied. So, the unity gain frequency of the single stage op amp used for the current control voltage source in the two stage op amp equals GM3 by CL. Okay. And this clearly has to be more than that one, so that the two stage op amp itself works properly. In fact, for the two stage op amp we did a rigorous analysis, found the second pole, and this is the approximate value that we got. Okay. This is the value that we got. Here I am only going through the intuitive stuff. In fact, if you evaluate the expressions you will see the exact condition, but what this finally says is the innermost op amp should have a unity gain frequency that is more than the unity gain frequency of the inner op amp, which has to be more than the unity gain frequency that you are trying to realize. Okay. So, this also points to some constraints. Like I said, this is only an approximate description, because now the transfer function of this can be quite complicated. You will have a third order denominator and also you will have two zeros because of these parallel paths through the capacitors and so on. It is not very easy to figure out where those zeros are. Okay. Intuitively you can do it analytically and then do it quite easily, but intuitively this condition has to be satisfied. The unity gain frequency of the innermost op amp has to be more than that of the one outside it, and which has to be more than that of the one outside it. Okay. And if you have more stages, let us say you go to 5 stage op amp, then you also need to have the innermost, which is I will call GM5 by C5, which has to be more than let me write it separately, GM5 by C5 has to be more than GM4 by C4, which has to be more than GM3 by C3, GM2 by C2 and GM1 by C, and C5 is nothing but the total load CL. Okay. Now, this condition also points you to some general constraint, that is, as you make op amps with more and more stages, you can only realize lower and lower unity gain frequencies, because typically there is an upper limit to GM by C ratios that you can realize, because what happens is even if you do not have an external load, the transconductor itself will have some capacitances, and the ratio of GM to its own inherent capacitance, there is a limit in any given technology. As you go to smaller and smaller CMOS processes, this limit goes on increasing, but there is always a limit. Now, given that the highest one, let us say you place close to the limit that is possible, that is the ratio of GM to the inherent capacitance is the highest that is implemented, then you have to maintain all these things to be successively smaller. So, that means that the highest unity gain frequency you can make a 2 stage op amp with is higher than highest unity gain frequency you can obtain for a 5 stage op amp. Okay. So, that is also the reason why you do not go crazy with the number of stages, although the higher number of stages will give you more DC gain, you only use the required number. Okay. So, 3 is practical, maybe 4 and 5 are done, but not so often used, and higher than that at least I have not seen. Okay. So, that is how you design multiple stage op amps, and because, by the way, this kind of a 2 stage op amp which has the C2, and we earlier described C2 as being Miller multiplied and loading the first stage, is known as a Miller compensated op amp. The 2 stage op amp that we discussed is a Miller compensated 2 stage op amp. Now, you see that first of all the op amp inside has a Miller compensation, the outside one also has a Miller like compensation. So, this entire thing is called the nested Miller 3 stage op amp. There are many variants of this to enhance stability and so on, we will not discuss any of those things, and just like we inserted a resistance in series with this to eliminate the 0, we can also try inserting resistances in series with that and this as well in various combinations. All of the results of this has to be obtained from more complicated analysis and simulation. I will not discuss those things except to say that that can be done. Okay. And there are lots of variants of this, because now you have more poles and zeros, there are also more ways of trying to get rid of them. You can see the papers in the journal of solid state circuits or transactions on circuits and systems for details of those things. The one thing I want to summarize here is that you can make multiple stage op amps when you need higher and higher DC gains. Let us say you want a DC gain of close to 100,000 or a million, that it is not possible to do with even 2 stages, you may have to go to 3 or 4 or 5 stages. Okay. It is possible, but stability becomes a bigger concern because of more poles and your maximum realizable unity gain frequency reduces. Okay. We started with a single stage op amp and we tried to make it better by passing the output current of the transconductor through a current controlled voltage source instead of directly through a capacitor, and that gave us a family of op amps that was better than the single stage op amp. Now, there is an alternative idea which also we can use, that is this we traces back to the original discussion on negative feedback circuits. Okay, that gives a entirely different kind of op amps which also are of interest in many cases. Okay. First of all, let me consider the non inverting amplifier that we designed long back. Okay. This is the input to the op amp, that is the output, and that is the input to the amplifier. Now, let me place a single stage op amp here. And this could have an output resistance G01 or GM1, let us say. Okay. And I will use a buffer to isolate these things just for simplicity, but there will still be a DC gain limitation because of G01 itself. Okay. This is VO, and because of this finite DC gain, even if you have a constant voltage, V is not 0. Okay. So, what happens is, to support a certain output voltage, you need to have a certain voltage across G01, which means that there has to be some current flowing through it. Okay. And to have some current flowing through it, you need to have some voltage across this one, that is the problem. So, in steady state, let us assume a constant input, there will be a difference between those 2 points, okay, when you implement this. So, this is the same as this particular amplifier with a DC gain of GM1 by G01. Now, let us go back to the basic idea of negative feedback. What did we say had to happen? Basically, in order to control some value to a desired value, we compared the desired and actual values and then drive the output based on that one. Okay, that was the basic idea. Now, we know that this voltage, which should have been kVi, will settle to a value which is less than that, which is kVi by 1 plus k by A naught. Okay. Now, the actual voltage is smaller than this one, and we can increase that by pushing more current into GO1. Okay. If we somehow manage to push more current into GO1, we will make this voltage larger and consequently the error smaller. Now, what is the desired outcome? In a negative feedback system, the feedback quantity here must be exactly equal to that quantity there. In fact, with an ideal op amp that was happening, right. If you had an integrator without a finite DC gain, this is what was happening. Okay. There should be a capacitor here C1, that is what was going to happen. What we can do is, this is the actual value, we can compare it to the desired value and based on that control the current that is flowing there, okay, using an integrator. So, what we will do is, we will take that, compute the error between the two. Okay. Now, if Vi is more than this value, that means that there has to be more current flowing into GO, okay, in from top to bottom. So, what we will do is, we will have an integrator and somehow make that push a current into GO, okay, that is the idea. So, in other words, just to summarize again, this feedback loop settles with a steady state error between these 2 points, okay, when we use this kind of an op amp. So, what we will do is, we measure the error between these 2 points after it is settled, let us say, and then we integrate that error further and inject a current into this output conductance. So, once the current through the output conductance increases, this voltage goes up, this also goes up and the error will become smaller. It can even become 0 if this integrator is ideal, right. It is very clear, if this goes on integrating when the input is non-zero, the only way to reach steady state is when these two inputs are equal to each other or the input to the integrator is 0. Okay. Now, this gives a different class of op amps known as feed forward op amps, which we will discuss in the next class. Now, one other thing that we can guess right away is that we are assuming that the original circuit reaches steady state and based on that steady state error we are doing the integration, but the integration itself is a continuous operation. What this really means is that the second integration that we have here is much slower than the first one. Okay. It almost looks as though the first one reaches steady state and based on the steady state value we inject some current here. Okay. In reality, what will happen is, the original one is going through its integration and this is going through its integration all simultaneously. It is just that this integration has to happen slowly enough, so that it appears as though the first one, the original loop has reached steady state and you are measuring the steady state error, based on that injecting a current into G0. Okay. We will see the details of that in the next class.